All right, welcome back to this next lecture. And we move on to chapter 2. And we start with chapter 2.1 and chapter 2.2. And this part is called Information and Conditioning. It's actually working towards a conditional expectation. Before you start with this, make sure that you master all the material from chapter 1. Yeah. So we will first look at information and Sigma algebras. So let's start. As the title indicates, we want to quantify information in a mathematical way. And we will do that with the help of Sigma algebras. Before we go into the formal definitions in a rigorous way, let's start with an example to motivate the idea. Yeah. So we will flip a coin 3 times. So we flip a coin 3 times and we look at the outcomes. And in that case, it's easy to define the outcome space. The outcome space is the set that we will call big omega. It has 8 elements. So again, suppose we flip a coin 3 times and let's look at the 8 outcomes, head or tail for each of the outcomes. So we end up with big omega being head, 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 HHT, HTH, THH, HTT, THT, TTH, and TTT. So, of course, we don't know beforehand which of these outcomes will result. But here, let's assume that we only have partial information given. Suppose suppose I tell you only what happened in the first coin toss. I'll tell you whether it's a head or a tail. And then I can quantify this information by the Sigma algebra, and we denote it by this calligraphed F here. So after one coin toss, we have F1. And F1 consists of the following. So after one toss, we have AH. And AH stands for, the first one is an H. So that stands for HHH, HHT, HTH, and HTT. That is written down as AH. And also we have HT, which is then equal to all the outcomes starting with a T, THH, THT, TTH, and TTT. And because we'd like to make a Sigma algebra from it, we need to add the empty set and also the full set omega. Yeah. So again, F1 is the information from the first coin toss. And it is a Sigma algebra. But I can give you more information. For example, I can tell you the outcome of the first 2 coin tosses. So if I gather that information, we will end up with F2. And F2 consists of, well, the first 2 coin tosses. They can be HH, giving rise to event AHH, AHT, ATH, and ATT. That is the basis of our Sigma algebra. But in order to make it a Sigma algebra, we need to add the complements, right? So let's add the complements. That is AHH complement, AHT complement, ATH complement, and ATT complement. So we need those in this. And also we need the possible unions. So for example, we need the unions AHH with AHT, AHH with union with ATH, AHH with ATT, AHT with ATH, and AHT with ATT. And moreover, the one that is left is ATT with ATH. And again, to make it a sigma algebra, we need the empty set and the full set omega. And in total, we end up with 16 elements. And note that, for example, this first one, AHH with AHT, that is equal to AH, which we defined before. And the same for the last one, ATT with ATH, that is equal to AT. Right? So that is what we get here. And we can also have a F3 after 3 coin tosses, F3, that is the outcome of the 3 coin tosses, and we call that the power set omega. Yeah, that's the power set omega. And it's clear that information is then captured by a chain of sigma algebras. And we call a chain of sigma algebras a filtration, because here it's clear that F1 is contained in F2, and that is contained in F3. Yeah, let's now make a formal definition of the sigma algebra. Let omega be a set, and we need here a time, capital T. We mainly need it for financial mathematics applications. Remember from lecture 1 that we had a final time for a contract or an expiry date, capital T, positive. And this can in principle be an infinite time, and then we don't need it. But for now, let's say we have a capital T, and we say a collection script F small t, where small t runs between 0 and capital T. That is called a filtration if the Fs is contained in Ft whenever S is less than T. So we interpret Ft as the information up to time T. Yeah. Now, in applications, we are usually interested in the information generated by a random variable. Like we are interested in sets of the form X is in B, X is in B. Remember that X inverse B is then more explicit, the set of all outcomes. That when we evaluate X on that outcome, it is in B, and B is a Borel set. And if we keep it simple, like we often do in financial mathematics, you can think of B as an interval. Yeah. So again, in applications, we are usually interested in the information generated by the random variable X. Like given a Borel set B, we ask ourselves, is X in B? Which is shorthand for little omega and big omega, such that X omega is in B. And this is the formal definition of the sigma algebra. Let omega F be a sample space or a measurable space. The book uses sample space. A measurable space is the notation in the case of measure theory. And let X be a random variable on omega, so that X inverse B, being X in B, is in F. Now, the sigma algebra generated by X is given by, suppose X is measurable, is given by sigma of X, X in B, such that where B is in the Borel sets calligraph B, X in B is such that B in B is contained in F. Again, where, as mentioned before, X inverse B stands for omega in big omega, X omega in B. It's not hard to verify that sigma X is a sigma algebra. This is because inverse images respect all the set operations. And we can verify if we have a sequence of Borel sets Bn, and I look at X inverse Bn, I take a sequence in sigma X. This X inverse Bn is in sigma X, and I look at the union. If I look at the union, I would like to have that this union is again in sigma X. because X inverse respects all sets operations, then this X inversion of the union, because each Bn is a Borel set, then the union is also a Borel set. And the result is indeed a set which allows you to be in sigma X. Yeah, so that is this line of reasoning. And the same for the complement. Yeah, so if I take such a set and I look at its complement in omega, this is actually X inverse of Bn complement. And this again lies in sigma X. So it's easy to verify that sigma X is a sigma algebra. Inverse images respect all set operations. And it is the smallest sigma algebra on omega under which X is measurable. So sigma X contains only information generated by X, while calligraphed F might contain much more information. Now, sometimes you might have a sub-sigma algebra of the original one that contains all the information of X. So it might contain also information that is not needed, but all the information that is needed in X sits in this sub-sigma algebra. In that case, this means that if we know in which G our outcome lies, then we are able to determine omega. So let's be more explicit in this case. So suppose G is a sigma algebra and sigma X is contained in G. Then we say X is G measurable, or in other words, X in B or X inverse B is in G for all Borel sets B. Note that if X is G measurable, then the information in G determines the value of X. So sigma X in this case is an efficient sigma algebra. It contains exactly all the information to determine X. G might also contain the information, but it may determine other information that is not relevant to X. So let's give an example to motivate this a bit better. Let's again take our 3 coin tosses, our 3 coin tosses as an example. Remember that F1 was the information up to time 1. And we have determined the information containing the information of the first coin toss. The 0, the empty set, the full set, AH and AT. F2, we have written it out in one of the first slides, the empty set, the full set, AHAT, AHHATT, etc. And F3 is the full information that was the power set of omega. Now let's give an example, and we take an example where we look at the price process. Yeah, so suppose on this sample space we have a sequence of random variables S0, S1, S2, S3 on omega, and we represent it by a tree, and later this could be something like a price process. And let's do it as follows. Let's say we start with S0, and that is equal to 4. And let's say each time when we have a head, the value doubles, and each time when we have a tail, the value shrinks. So if we have a head, S1 will be 8, and if we have a tail, S1 will be 2. Now again, for the second time, we can have a head, and we end up with S1 equal to 16, and we can have a tail ending up with S1 equal to 4. And here also we can have a head S2, sorry, this is S2, 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 S2 equal to 4. And if we have a tail, then S2 is equal to 1. And a third time from 16, having a head, we end up with S3 equal to 32. And with the tail, we end up with S3 equal to 8. From 4, if we have a head, then S3 would be equal to 8. And if we have a tail, S2 would be equal to 2. And here we can also have a head that would give us S3 equal to 8. And a tail would give us S3 equal to 2. And finally, here we can have a head, gives us S3 equal to 2. And a tail would give us S3 equal to 1. So we have a 0 in time 0 S is 4. In S1 we have 8 or 2. And in S2 we have 16, 4, 4 or 1. And S3 we have 32, 8, 8, 2, 8, 2, 2 and 1. So let's consider S2. And let's try to find the sigma algebra related to S2. Then it's enough now to start with the sets. We have S2 equal to 16, S2 equal to 4, and S2 equal to 1. And let's look at these sets and see what they are in particular. If we look what S2 is 16 is, it is the probability of 2 times head. The event that we have 2 times head, AHH. S2 is equal to 4 will give us, is given by us if we have the union of AHT, first head, and ATH, second head and first tail. And S2 equal to 1 is given to us by 2 times the tail, ATT. So if I have to make a sigma algebra out of them, then the sigma algebra, the sigma of S2, that is of course the empty set, the full set, and it is, so it's the empty set, the full set, it's AHH, it is this combination AHT union with ATH and ATT. Now, to make a sigma algebra out of them, we need the complement, so we need AHH complement. And if you think about it, that is the complement of AHH, that is in fact the union of AHT with ATH with ATT. And look at that a bit carefully, then you can see this. And the complement of AHT with ATH, that is in fact AHH with ATT. And similarly, the complement of ATT is the union of AHH with AHT with ATH. And that is together, that is contained in F2. In fact, it is smaller than F2. Yeah, it is smaller than F2. How can we see that? Well, we can see that because AHT, that is in F2, but it's not in sigma S2. Yeah? So AHT is in F2. However, AHT is not in sigma S2. So F2 is finer than sigma S2. And if we know where we are in F2, we can determine S2, but there is some redundant information that we don't need. So sigma S2 is the deposition sigma algebra that contains all the relevant information, and it is a subset of the bigger one. And in that case, the random variable would also be measurable with respect to the bigger one, of course. And this leads us to another concept, the concept of being adapted. So again, finalizing this notion, since F2 is finer, if we know in which element of F2 our outcome lies, then we know the value of S2. The same, of course, is true for sigma S2. Now we go to this, this new definition. Let omega F be a non-empty sample space, and let Ft with small t between 0 and capital T be a filtration. So again, remember filtration that Fs is contained in Ft is contained in F when S is less or equal to T. Now a collection xt with small t between 0 and t of random variables is said to be adapted to the filtration if xt is ft measurable, which means we know the information up to time t. By knowing the information up to time t, we can determine the value of xt completely. Yeah. So it's measurable with respect to the sigma algebras. So let omega f be a non-empty sample space, and we have a filtration. Then all you have to understand is that ft is enough to determine xt. Right? Now, the next concept I'd like to discuss is independence. You have seen this notion before, but now we use sigma algebras as well. Yeah. Before we start, let's motivate it. Yeah, we relate it to what we have done before. So when a random variable is G measurable, the information in G is sufficient to determine X. However, in contrast, when a random variable is independent of this G, then knowing the elements of G does not shed any light on the value of X. Yeah. So let's quantify this notion and remember that unlike the concept of information or measurability, where only sigma algebras are needed for the notion of independence, one does need probabilities. So let's start. There will be a chain of definitions. They are all easy to follow. So we start with a probability space. We relate it to what we've done before. We build the definition up bit by bit. Yes? So again, recall that two events A, B in F are independent if the probability of the intersection is the product of the probabilities. And that is what we have here. Omega Fp is our probability space. The two events are A and B are in F, and they are said to be independent if the probability of the intersection is the probability of A times the probability of B. Well, this gives us an interesting insight, namely if the probability of B is positive and we have independence, then independence tells us that the probability of A given B is equal to the probability of A. How can we see that? Well, we can see that as follows. The probability of A given B, that is by definition the probability of A intersection and B divided by the probability of B. Now the intersection of A and B, we just said this is, in the case of independence, the probability of A times the probability of B. We can divide it here by the probability of B, and that gives us the probability of A. And that concludes that statement. So this is for two events in F, and then, as I mentioned, we will generalize it step by step. We can extend this notion to sigma algebras and to random variables as follows. First of all, first one here, let omega Fp be a probability space, and now have calligraph G and H contained in F be two subsigma algebras. Then we say that G and H are independent if indeed the probability of the intersection of G and H, where G is in the subsigma algebra calligraph G and H in the subsigma algebra calligraph H, the probability of this intersection is the probability of G times the probability of H. Secondly, two random variables, x and y, again on our probability space, omega fp, they are said to be independent when the sigma algebras of x and y are independent. Thirdly, a random variable x on omega fp is said to be independent of the sub-sigma algebra calligraph G of f contained in f if the sigma algebra of x and G are independent. And all these definitions are related to two events, two algebras, and we can extend this notion of independence of a pair to any number of sigma algebras or random variables, and that is contained in the following on the following slide. Again, here we just generalize from pairs to multiple. Let omega fp be a probability space. Then the generalization 1 is the following. The sequence G1 up to Gn be sub-sigma algebras contained in F. They are independent if the intersection of A1 with A2 with etc. with AN is equal to the product of the individual of A1 times A2 times AN, to the product of the probabilities for all A sub I in GI, and I runs from 1 to n. Second, a sequence of random variables x1 to xn is said to be independent if the sigma algebras sigma x1 to sigma xn are independent. Third, a sequence of sigma algebras, calligraph G1, G2, etc. contained in F are independent if for all n, G1 up to Gn are independent. And fourth, a sequence of random variables, x1, x2, etc. They are said to be independent if for all n, x1, x2, up to xn are independent. There's another theorem, an important theorem that we would like to discuss, and that is based on that is related to functions of x and functions of y. And the theorem is as follows: let x and y be independent random variables on omega fp, and let f and g be Borel measurable functions. Then also f of x and g of y are independent. That is what the theorem says. And the proof is relatively easy, so we go through it. And what we would like to show is that the sigma algebras of fx and gy are independent. And the sigma algebra of fx is, so fx is in B, and B is Borel. And the sigma algebra of y is G, y is in C, and C is Borel. Now let's look at that first part. Fx is in B, that means that is nothing but little omega in omega, such that f dot x omega is in B, or in other words, we have seen that several times before already, and it is in detail written in the book, little omega in big omega, such that x omega is in F inverse B. And short notation is x is in F inverse B. And notice that F inverse B is a Borel set. And because it is a Borel set, hence the sigma algebra of Fx is contained in the sigma algebra of x. And this goes similarly for gy. Gy is in C. That means y is in G inverse C, and G inverse C is a Borel set. And therefore, the sigma algebra of G of y is contained in the sigma algebra of y. Now, since sigma x and sigma y are independent, it also follows that sigma of fx and the sigma of gy are independent. Now, we want to quantify independence, and we want to come up with some statements regarding independence, also with respect to distribution measures and distribution functions and densities. And for that, we need first the definitions of the joint measures and joint distribution functions and joint density functions. So we generalize the concepts of scalar random variables to vectors of random variables. So let x and y be random variables on omega fp. Now, first of all, first statement is, first definition, these are just definitions, the joint distribution measure of x and y, that is a probability measure on the product, the Borel set of the product R squared. And that is defined by mu sub xy of C is the probability that xy is in C. And again, written out, that is the probability that little omega is in big omega, such that x omega comma y omega is in C. The joint cumulative distribution function, the joint CDF, that is then given based on the definition of the joint distribution measure, capital F, F with subscripts capital X and Y, so the joint distribution function of X and Y, with as arguments little x and little y, that is the joint distribution measure on the space minus infinity to little x cross minus infinity to little y. And by definition, that is the probability that our random variable capital X is less or equal to little x, and our random variable capital Y is less or equal than little y, with x and y in R. We can go to density functions. So we have, suppose we have a non-negative Borel integrable function, small f, with subscripts xy, the joint density function, with independent arguments, again, little x and little y. We have that the double integral from minus infinity to infinity of fx and y dx dy is equal to 1. Well, this is a joint density for the pair xy if mu xy of C is the double integral of the integral of C of fxy dy dx. That is the definition. This is the definition of the joint density, where C is in the Borel set of the cross of the cross R squared. And in this case, the distribution function, the joint distribution function, the joint cumulative distribution function of x and y is defined as the integral from minus infinity to x and the integral from minus infinity to y of small f xy dv du, where v and u are the running indices. Now, in order to say something about independence, we also need to talk about the marginal distribution measures, the marginal distribution functions, and the marginal densities. So given this joint density, this joint distribution measure, mu xy of x and y, now the marginal distribution measure of x, of y, of A, is defined as the marginal distribution, is defined as the joint distribution measure of x and y on A cross R. And that is in more detail defined as the probability that x is in A where y is in R. So in fact, this is just the probability that x is in A. So this is the probability that xy is in A cross R, where A is a Borel set of R. Yes. So this is the marginal distribution measure of x. So the marginal distribution measure of x. And equivalently, similarly, we can define the marginal distribution measure of similarly, we can define the marginal distribution measure of y on B. And that goes really similarly. It's the probability of y is in B. And that is then the joint distribution measure of xy on the interval R cross B. And like we have marginal distribution measures of x and y, we also have marginal cumulative distribution functions, f of x and f of y. And they are defined as mu of x, the marginal distribution measure of x, on the interval minus infinity x, or another way of defining it is the probability that x is less or equal to little x and y is just in R. And similarly for the cumulative, the marginal cumulative distribution function of y, it is mu of y on the interval minus infinity to y. Now, if xy has a joint density, f of x, fxy, then we also have marginal densities of x and y, and they are given as follows. The marginal density of x is the integral over y from minus infinity to infinity of the joint density fxy dy, and the marginal density of y is the integral over x of minus infinity to infinity of the joint density fxy dx. And moreover, we know that the marginal probability measure of x on A is the integral over A of fx dx, and the same for the marginal distribution measure of y on B. It's the integral on B of fy dy. Now, with all these definitions, we can say something about independence. And in the book, this is done in detail in theorem 2.2.7, where we characterize independence in terms of a joint distribution measure, in terms of the cumulative distribution function, and in terms of joint densities. Moreover, it's also done in terms of the so-called moment generating function. So the following statements are equivalent. So x and y are independent, with a focus on independent. That is equivalent to saying the joint probability measure of x and y on A cross B is equal to the marginal probability measure of x of A times the marginal probability measure of y of B. Third, the joint cumulative distribution function of x and y is, in the case of independence, equal to the marginal cumulative distribution functions of x times the one of y. Fourth, we go to densities. If xy have a joint density function, fxy, then independence is equivalent with fxy is equal to fx times fy. The joint density function in the case of independence is equal to the product of the individual marginal densities. And then finally, we come to that moment generating function. The moment generating function is defined by the expected value of e to the power ax. Yeah? E to the power ax. And if we look at that in some more detail, we see that the expected value of e to the power ax, and sometimes it's denoted in the book by phi sub x of a, that if we write it out with the Taylor expansion, then this is equal to the expected value of 1 plus ax plus a square over 2 factorial x square, etc. And the expectation of this term. We can take the 1 out of the expectation operator, and we use the linearity, and a is a constant, so it's 1 plus a expected value of x plus a square over 2 times the second moment. And you see all the moments appearing, the first moment, the second moment, etc. And it is even the case that by means of a moment generating function, where all the moments are being defined, the distribution function is uniquely determined. Now, independence means that e to the expected value of e to the power ax plus by is then equal to the individual moment generating functions. The expected value of e to the power ax times the expected value of e to the power by. Now we end up with some facts. So when x is normally distributed with mean 0, so in expectation x is equal to 0 and variance t, then in other words, this means that the density is equal to 1 over the square root of 2 pi e to the power minus 1/2 t square over t. And then in that case, it is easy to show, and try it yourself, that the moment generating function is given by e to the power 1/2 a squared times t. Of course, we know that the variance is given by this. We write variance of x. It is the expected value of x minus its expectation squared. And we have already seen, and we know that this is larger or equal to 0. And the standard deviation, that is just the square root of that variance. Now we look a little bit further, a little bit more into independence. And let's look at the covariance. The covariance of x and y is defined as the expected value of x minus its expectation times y minus its expectation. And if we write that out in using just the properties of the expectation operator, we will end up with the expected value of x times y minus the expectation of x times the expectation of y. Now, if x and y are independent, then we know that the expectation of the product of x and y is equal to the expectation of x times the expectation of y, provided that the expectation of x times y in absolute value is finite, exists, so is less than infinity. Well, substituting in the case of independence this expression for the expectation of x times y, we see that the covariance is equal to 0. So in the case of independent variables, then the covariance of x and y is equal to 0, and we say that x and y are uncorrelated. The converse, however, need not be true. And a typical quantity that is very useful and handy in this respect is the correlation coefficient Rho, denoted by Rho of x and y, which is defined as the covariance of x and y divided by the standard deviation of x times the standard deviation of y. And this correlation coefficient, as you may know, lies between -1 and 1, where -1 means perfect negative correlation and 1 represents perfect correlation. Well, this concludes this 45 minutes, and see you in the next 45 minutes.